Hello, my name is Elizabeth Bennett, and this is my Physics 2211 Lab 2 report. The purpose of this experiment was to record and analyze the motion of a falling object starting from rest that travels along a path with variable velocity due to the force of gravity and drag acting on the object. The motion of the object was tracked using the tracker software to develop a graph of position versus time of the object. The model used to create the predicted data was a glow script code modeling the path of the object. One code takes into account only the force of gravity on the object, while the other code factors in both the force of gravity and the effect of drag. The fundamental physical principles used in this lab is Newton's second law, which states that force equals mass times acceleration. Newton's second law also relates the velocity and position update formulas, as net force is used to determine the updated velocity, which is then in turn used to find the updated position. Drag is also used in this lab, the force of which can be calculated as negative b times the instantaneous velocity squared. The main results of this lab were that the observed position versus time graph and the predicted data taking into account both gravity and drag are very similar, while the predicted data only taking into account gravity has a very different slope and shape. This experiment involved the dropping of a coffee filter from 1 meter above the ground to the floor. The coffee filter's motion was tracked using the tracker software to create a position versus time graph. The system in this experiment is the coffee filter, and the surroundings consist of everything else, including the force of gravity acting on the filter and the air pushing against the filter, creating drag. The initial position of the filter is at 0, 0, based on where I place the axes in the origin in tracker. The initial velocity of the coffee filter is 0 meters per second because it was dropped from rest. This first program predicts the motion of the coffee filter while only taking into account the force of gravity and ignoring the force of drag. First, the mass of the filter was set to be 0.00086 kilograms. The original position of the coffee filter is at the origin, or 0, 0, as previously mentioned. Additionally, the filter is traveling in the negative y direction. The path of the coffee filter was started at time equals 0 seconds, and the position was taken every 1/30th of a second. G is the force of gravity near the Earth's surface, which is 9.8 meters per second squared. B is equal to 0 in this code because the force of drag is being ignored. The condition of the while loop is that the loop will continue as long as t is below 1.5 seconds because the path of the filter was tracked for 1.5 seconds. The net force acting on the filter is equal to the mass times acceleration, or in this case, negative 9.8 times 0.00086 kilograms. Based on this calculated net force, the updated velocity can be calculated using the velocity update formula, which is the initial velocity plus the net force divided by the mass, all multiplied by delta t, which is 1/30th of a second in our case. Next, the updated position can be determined using the new velocity and the position update formula, which is the initial position plus the new velocity multiplied by delta t. Then t is increased by delta t, and the loop runs again as long as t is still less than 1.5 seconds. This second code is the same as the previous, except this model takes into account both the force of gravity and the force of drag. Thus, the proportionality constant for the magnitude of the drag force is 0.015 instead of 0 as in the last program. Additionally, the force of drag is calculated as the proportionality constant b times the magnitude of the velocity of the filter squared times j hat. The total net force is calculated by adding the force of gravity plus the force of drag. The three position versus time graphs on the left side were combined to form the position time graph on the right, comparing all three datasets. The bottom left position time graph is based on the observed data as evaluated by tracker. The top left position time graph is based on the predicted data only taking into consideration the force of gravity, and the middle left position time graph is based on the predicted data taking into account both the force of gravity and the force of drag on the filter. The observed position versus time graph and the predicted data taking into account both gravity and drag are very similar, with fairly linear shapes and similar slopes, as they continuously overlap. The predicted data taking into only account the force of gravity looks very different from the two previous graphs, as it has a much steeper slope and an exponential shape. This makes sense because gravity is pulling the filter down at a constant acceleration. However, gravity is counteracted by the force of drag as air pushes up against the coffee filter. Therefore, the filter will fall much slower because the air is pushing up on it, slowing it down. The observed data and predicted data based on gravity and air resistance have slight variations that could be due to the fact that only the vertical position of the filter was taken into account, but the filter did not have a perfectly vertical fall, just because of its shape. Additionally, the value of b used in the code for the proportionality constant of the magnitude of drag was estimated and does not perfectly represent the force of drag on the filter. The observed and predicted data taking into account gravity and drag predict a terminal velocity because the terminal velocity is the velocity that the object reaches so that the acceleration or net force is constant. On Earth, this acceleration is negative 9.8 meters per second squared due to gravity. Thus, an object reaches its terminal velocity when the mass and air resistance cancel out. The predicted model only taking into account gravity cannot model this because it does not model air resistance. If the object was thrown down, the terminal velocity would remain the same because it is determined by the mass equaling out the air resistance so that a constant net force acts on the object. The initial velocity does not affect the terminal velocity.